camera, which is, say, for example, designing the camera, telescope, or optical sensors, which requires transfer of image from A to B, or even LiDAR and so on. Another tool which we are dealing with is from another company called OptiLayer GmbH from Germany. This is mainly to design the thin film, which consists of 3 tools like OptiLayer, OptiRay, and OptiChar. We also deal with the RP Photonics software tools, various tools like fiber power, fiber calculator, Resonator. These are mainly for designing the fiber and traditional lasers and amplifiers. Now, coming back to the Synopsis, Synopsis, as most of you who are working on the EDA tools must be aware that Synopsis is the biggest company, multinational company, to deal in the EDA tools, like on VLSI and so many other products, thousands of products Synopsis has. Synopsis is a 3.6 billion company with about 14,000 employees world over. That includes the India, and large number of patent and almost 130 offices. So originally, Synopsis was an EDA company purely dealing with the electrical domain, but around 2009-10, it was realized by all technology companies that technology cannot progress without support of optics and photonics. So Synopsis ventured into optical field. Before that, it was purely working on the electrical domain. So in 2012, they acquired a company called Optical Research Associate, which was dealing in the ray optics tool, that's light tool and code 5. Then in 2011, then 2012, they acquired a company named RSoft Design Tool, which was in the photonics device and system tools. Later on, they acquired one more German company called LucidShape, again on the ray optics tools, mostly in the automobile optics. And in 2018, they acquired Netherlands-based Phoenix, which was in the Synopsis, which is in the PIC tool, offering PIC tool called Opto Designers. So now Synopsis is the only company which has vast portfolio of photonics and optics tools, and particularly on the photonics side, right from the device level to the circuit fabrication level, they have all the tools. And their EDA tools like CentOS, TCAD, all of them can co-simulate with photonics tools as well. So it's a very big advantage to the user. Synopsis Optical Solution Group has several offices across the world. Okay, so now one more thing, this Synopsis optical and photonics products are dealt by what is called the Optical Solution Group. And this Optical Solution Group has a separate channel of marketing, and it's kind of a subsidiary within Synopsis as far as marketing and product support concerns. So we are dealing with all optical and photonic solution products. So today, I'll introduce you to the RSoft photonic device design software and photonic system design software. Now, this is the roadmap or the product map of RSoft Photonics design software. This is the device tools. We have number of device tools, to be precise, 7. And there are 3 optical communication system design tools. Apart from the 7 passive device tools, there is an active device tool called laser mode. And apart from that, there are number of utilities. Now, these are the simulation engine based on different techniques to solve the different kind of a structure and different problems in the structure designing. The utilities are essentially, they are not the simulation engine. They actually utilize the simulation results from these tools and do the post-processing for a specific purpose. Say, for example, solar cell, as the name indicates, it is mainly to design the solar cell and the calculate and various design parameter for the solar cell. As similarly, LED and so on. So which we'll see in today's presentation. Unlike other companies, all the Synopsis tools are based on the different techniques. Essentially, they are all solving the electromagnetic equations, but they are based on the different techniques. Some of the companies do have different tools by name, but they're probably like somebody is using only Fdtd in different form to solve the different structures. Synopsis has a number of different techniques to solve the various problem in the photonics devices. And each of the methods has their own pros and cons. Like coupled mode theory, when we are going for the coupled mode theory, it is very efficient and very simple and very speedy simulation process. But if you move towards the FDTD, so it is very accurate and very versatile, but then it takes a lot of computational resources and takes a lot of time to simulate and may not be suitable for bulk devices. Bulk in the sense in the photonics terms, not the realistic terms. So these are the different methods and techniques which we'll see in the next slides of presentations. These are the tools which I have already described. BeamProbe BPM mainly suitable for the fiber and waveguide devices, full wave for the photonics nanostructure. And these are the last letter basically indicates the techniques that they are using, like plane wave expansion, Bandsaw, and that is suitable for the photonic crystal devices. Grating mode based on the CMT, suitable for the grating structure. Diffract mode based on the rigorous coupling wave analysis for the diffractive grating structure. FAMSIM is a general mode solver. Mode probe, Eigenmode Expansion method-based tool, again for the mode solve, and sometimes can be used where you need the FDTD technique. The active device tool called laser mode is for the semiconductor lasers and the detectors. The utilities for the LED utilities, LED extraction structure, solar cell utility for solar cell design. Most is an unique tool with the RSoft Photonics device tools, which handles uh, multi-variable optimization and scanning. So it automates the design variations which you would like to simulate automatically, and gives the either the scanned result, or if you want to optimize a device on a specific parameters, it will do that. It also includes multiphysics utility to count for the stress, carrier, electro-optic effect, and thermo-optic effect. And then the tapered laser utility, which is, as the name indicates, to design the tapered lasers. Now, this tapered laser utility, again, as I said, this utility are using the optical simulation by the tools which we have described earlier. Now, what is the photonic devices? As all of you know, since all of you are working on the photonics field, in simple term, it's creating and manipulating or detecting the light, modulating a beam of light, combining and separating the beam of light in a different wavelength. When light is just manipulated, not created, we call the device dealing with it as a passive device. When the light is created within the device, we call it, or the light is detected, we call it the active devices. This is the design flow of RSoft software. This design flow is common for all the tools. Now, RSoft CAD is the common CAD tool for all the passive device simulation engine, which I have described earlier. All the 7 passive device tools are using the same CAD. So what you can do with the CAD is define the geometry. You can draw the geometry. You can actually draw the geometry, define the material in each of your device zones, and define what you want to simulate. Then this information is passed on to the simulation engine, which you are going to use, whether it is BPM based or Fdtd based or CMT based, whatever you have decided in the first step. Then once the simulation is done, there is a post process, and all of them are again using a common graphic software called WinPlot to output the data. So this is how the RSoft CAD looks like. I'll also switch back and forth between the presentation and the actual software to give you the idea. All the devices, all the device simulation tool are installed at one time. In fact, now the entire Photonic suite that includes the RSoft Photonic device design tool, RSoft or the Photonic system design tool, and PIC tool. Now they have the one single installation EXE. But only those tools will work for which you have the license. So you can draw your geometry over here and take the output using the WinPlot. This RSoft CAD also can import or export the mask layout directly for the individual devices or couple of devices. and it can interact with the other third-party software also. RSoft is, as I have mentioned earlier, the CAD is shared by all the tools. One device which you have simulated using the beam probe, the same device, if you want to simulate using the Fdtd, you just have to change the simulation tool from the setting. This is how the tool looks like. I'll also show you the actual tool. These are the different drawing tools, the geometrical drawing tools, which you can use to draw any type of device or any type of arbitrary structure, and then define their parameters. These are the variable creating tools, and this is the simulation tools. And these are the menu bar like file opening the graphics and so on. Initially, when you open the file, a global setting box dialog box will open, which is shown here on the left-hand side as a symbol of Earth. And here you can select what simulation tool you want to use, whether your device is 2D, 3D, you want to do the radial calculation, and you can also do the global settings or the default settings for the refractive index, free space wavelength. In case of 3D structure, what kind of 3D structure you want to use, and what is the initial viewing. This is what is called the global setting. But for each of the segment, you can define the properties separately also, that we'll see. On the top, this indicates what tool you are using, what view you want to use, whether you want to use X, Y, or Z view or 3D view, or you want to use all the four together. Then zooming and what is the cross-sectional area and so on. This is again the, as I have already told, global parameters, symbol tables, and so on, which I will discuss about this once I will show you the actual software. These are the different simulation tools, the launch field, the pathway, a simulation button, and then displaying the index profile, using the most, and mode calculations, and so on. RSoft CAD has a 3D editing options. When you have a 3D device, you can view all the cross-section simultaneously, and also you can view the 3D view, and you can also open the 3D view separately. RSoft CAD designs the structure, any kind of arbitrary structure with different segment, and each of this segment, all the parameter can be defined in terms of the symbols. So if you are using the same parameter in multiple segments, you need not change that value in each of them. Rather, you are defining that parameter as a symbol, and just by changing the value in the symbol table, that change takes place in all the segments. the structure which is designed in the RSoft CAD, it can be divided into various segments, and each of the segment will have the separate property window. So each segment you can define different optical properties, various references, and different material. RSoft CAD allows to design the multi-layer structure. Either you can design the multi-layer structure by individually putting different layers together one by one, or you can use what is called the multi-layer editor, and using the layer table editor, you can define the different layers in the multi-layer table, in the multi-layer structure. It also has an array layout utility. Now, when you want to design a periodic array, this array layout utility has so many options. You can design 2D, 3D array, and with different type of units. Any type of custom structure can be defined in the RSoft CAD. Also, once you have a unit file, you have designed one structure. That structure can be embedded into another superstructure, and so there is an hierarchical design in RSoft CAD. RSoft CAD allows the calculating of index before you actually do the simulation, because if you have certain structure in mind, and if there is a mistake in drawing the structure, the all simulation results will be very wrong. So before actually simulating this structure, you can see the index profile of the design structure, whether the index profile is correct and what it was intended for. RSoft CAD. Now, whatever I am describing here, these are all the features of RSoft CAD, that CAD which is common for all the tools. So I will also be a little in detail once we go into the simulation software, because these features are being used by all the tools, all the passive tools. RSoft CAD has a material editor where there are lot many materials are available by default, and the user can add any material. It has various tabs to define the material, and this material can be used in the structure. And each of this material, like if any of the material, you can see that what is the dispersion characteristic or index characteristic based on whatever parameter has been defined over here. So if you are defining your own material, you need not put all the fill all the tab. If you are defining a semiconductor material, you just need to define the properties where there is semiconductor material defining property. All the file which is designed in the RSoft tools, they are saved as a .ind files, and all this can be opened in the ASCII format. So you can view what actually that design is. Okay, so now I think I will go to the, actually I'll open the tool. Can you see the tool? Is it sharing? Are you able to see the tool?
Yes.
Okay, okay, okay. Okay, this is how the RSoft CAD will look like when you open. These are the different geometry shape which you can use to draw. When you open a new file, it will open a startup window or the global parameter. Now, these global parameter are default parameters. If you have not defined any parameter to any segment, these parameters will be used and also will be used for the background. Here you can select what kind of simulation tool you want to use, what is the dimension of your structure, what is the free space wavelength you want to use, and refractive index and different component width and height and so on. Okay, so once you say okay, these are the tips which you will keep on getting. Now, this is a new project. Here you can select and draw the structure. These are the different structure. Now, since we have defined it as a 2D, we are drawing it the 2D options. Okay, now I'll just delete this. This structure which we have drawn here, if you right click on it, it will open the segment window, segment property window. Here you can define the material. The material library will open where you have different type of material and you can select any of the material and define to that particular segment. Now, if for this ITO material, if you want to see this is a default material given here in the library. If you want to find out what is the index for this, you can check over here. Okay, and so on. So there are different tabs, and each of the tab are defining the different properties. But when you are installing, when you are in defining your own material, you need not put you need not fill all the tabs. Only the tabs for which is applicable to your material or you want to use it in the simulation are required to be defined. Okay. Now, this also material, either you can define the material from the material library, which is new material, and this is what we have seen, or you can define the refractive index over here local. This is the starting vertex and ending vertex refractive index. This is the reference positions of the this particular segment. Now, when you have multiple segment, say for example, if I am drawing another segment, for this segment, I want to make sure that between these two segments, there should not be any air gap. There are where one material ends, the second segment should start. So here you have the offset, which offset you can say with reference to component 1, the offset is 0 in X direction or Z direction or so on. Okay. And each of them, each of the segment can have the different property. This can have different material than this one. Okay. Now, okay, sorry. Now here, this is the symbol table. As soon as you create as soon as you create any sorry. Okay. As soon as you create any segment, it will automatically define some variables. User can also introduce their own variable and define it over here and use in the structure design. Then this is for the multi-layer. If you are using a multi-layer structure, then this can define the various layer of the structure. This is a simulation, performing the simulation. What you want to here right now we are using the beam probe, and what is the simulation domain, which mode you want to simulate, and so on. This is the before you want to, if you want to calculate the modes, what are the modes supported in this particular device, or you want to see the material profile of this particular device, and this is the simulation. And this is the pathway, defining the pathway, launch field, and so on. Now, launch field, you can define different type of a launch field. Either you can select any of this, or you can define the launch field from the file. You can define the file format, the measure data of any field, and use that here for the launch. Now I'll just show you in the RSoft CAD. It can, as I was saying during my presentation, it can handle any kind of a complex material. Okay, this is a 3D structure. Now, as you can see, this has lot of uneven shape. This you can each of them has a separate, can have the separate property. On you can this all any kind of arbitrary structure can be defined in the RSoft CAD. You just need a little bit innovations to define and design the any kind of a structure. Now here, this as you can see, this is a complex structure, but still it is, you don't have to draw the full structure. You can design each of them by one, and by defining the this structure, actually you are replicating over here by changing the angles. And if you go to the symbol table, now you will see here there are a lot of symbols which are defined for this structure. Okay, so it can you can define different kind of structures like this. These are the 3D structure. All of them can be defined in the RSoft CAD. This is another kind of a structure which can be defined. So you can actually see what you are what you have planned to define, and whether the structure looks like exactly the way you want to do. Yeah, okay, fine. These are the simple structures. Now we'll go back to the presentation again. Okay. Okay. Maybe I'll show you the files as well. Now, if I open this is IND file. You can see this is nothing but an ASCII file. So you have the user has access to all the data. If there is an expert user, you can even modify the structure from ASCII file. This is the as I have shown you, the different kind of 3D objects can be simulated in the RSoft CAD, or rather can be designed. Okay, so now next we move to the beam prop tool. The beam prop is basically based on the beam propagation technique, which so many of you are aware of. It solves the Maxwell equation with a steady state with no time data. In beam probe, only one wavelength travels at a time, and light must travel in one direction. So this is what is BPM based technique, and it is suitable for the waveguides, WDM multiplexing devices, modulators, or multi-mode interface devices, splitters, couplers, and standard and specialty fiber design. This is very fast simulating tool, can handle big structures, but you don't get time dependent information. So what you get is essentially more, and you can also find out various laws and etc. So BPM based tool solves the well-known parabolic or paraxial approximation of Helmholtz equation. It computes the propagation of light wave in arbitrary waveguiding geometry. Any kind of arbitrary waveguide can handle. Uses the transparent boundary condition, means the light is lost. The BPM calculates the field distribution of structure made in the CAD interface. So whatever you design and define in the CAD interface, BPM simulation engine automatically reads the structure. In fact, this is the design process for all the tools. First, you define the geometry, draw the geometry, assign the material property for each of the segment, define the optical source, as I had shown. The input source, you can define whatever type of input source you want to use. You can define multiple source as well. You can define the source at the location where you want to use it, and then set the desired measurement parameters, algorithms, and run the simulation and then view the results. This is true for all the RSoft CAD tools. In beam prop, it has two methods. One is correlation and another is the iterative methods. In the correlation methods, it records in the first propagation, it records the Fourier transform to be obtained and identify the resonance, that's N effective. And in the second propagation, it will find mode field profile at all the calculated N effective. Now, benefit of this is obtaining all mode at once. This is also valid for the leaky mode. It finds the bending modes through the index mapping technique. In case of iterative method, it will propagate along the imaginary axis or the lossy axis, and all modes exponentially grows. Fundamental grows the fastest and dominates. So the solved mode is removed from the field, and then next higher order mode is found. So the modes are found one by one, but if you have a small number of modes, then this is a faster method to solve, but not valid for the leaky mode. Now, this is an example of Mach-Zehnder interferometer in the using the beam probe. So you have the two arms, the light is incoming. Now, if both arms are equal at the output end, the both beam will combine and you will have output light in the same phase. But if we introduce some phase shift in one of the arm, then the light, both the beam will not have the same phase, and there may be a destructive interference. Okay, so this can be, this is a beam probe simulation, and I'll show you. This is just one 3D waveguide. These are the beam probe solutions. I'll show you the actual software, and we'll simulate one of the beam probe example. Now, this is a coupler. Now, as you can see, this coupler has 1, 2, 3 segments in each arm, and all of them are drawn using the different geometrical structure from here. Like this arm, this particular part is drawn using the S-band. This is a straight, simple waveguide. This is again the S-band. Okay. In beam probe, then you have to define what is called the path. So you have to define the path, or rather it's nothing but putting up a measurement device and defining where you want to measure. So there are two paths defined in this particular device. This is path 1 and this is path 2. Now each of the path will have, you have to put the monitor to measure whatever quantity you want to measure. So if we go to the path, this is path number 1. Now find out what is the monitor. You can introduce a monitor over here, and monitor can be of different type. Okay, these are the different type of monitors available to be used in the beam probe. The monitor position you can define here. The whether you want to have this monitor tilted or straight and so on, and what modes etc. you want to detect, that all also you can define over here. Okay, so in this case there are in this case there are two path wave, and each path wave has a monitor. This is the monitor number 2. This measures the slip power, mode power, and so on. So now let's simulate this device. First, you can compute the mode and see whether the mode profile is, or the rather index profile is the same as what you have desired. So if you calculate this, this is at Z is equal to 0. That means over here, this is a Z axis, this is X axis. One more point I would like to point out is in RSoft, Z is the direction, default direction of propagation. X is the width, and Y direction is if you open the property window, Y direction, this is 2D device, but otherwise the height is not the height in the common sense, but this is the dimension in the Y direction. Okay, so this is a 2D device, there is no height. And here, as you can see, there is a input source. This is a slab mode, which is being used for this input of this coupler. Okay, now let's simulate. As you can see, beam enters here and then it divides, and a majority of the beam travels into the second arm. So it's like 10-90 kind of a ratio for this coupler. Now, these, if you want to see the results, in the 3 dimensions, you can open the 3 dimension, how the power varies and so on. So these are the various options available for the measurement. So beam probe is mainly used for the simulation of simpler, bigger devices. This is a switch. Now, if you simulate the switch, it will show you how. Sorry. How the power is traveling through. And you, as you can see, although this is a simpler device, but as you can see how the power is propagating and is input at this port is coming out at this port. Now that is all depending on the design of this particular switch. So beam probe is used for this kind of various devices. Now let's move to the next simulation tool, because we have so many tools, and full wave. This is the full wave Fdtd is based on the finite difference time domain method. And as you all know, that Fdtd carries the time dependent information with it. So there is no physical approximation. The entire structure is divided into so many meshes. And here, Fdtd, the problem size is limited by the computing powers. So since it's a very computational, it requires very high computational resources, you will need really good resources for the computation. So normally Fdtd is used for nanostructure, very small structures where you need the time dependent information. A typical application is to simulate LEDs, solar cell, switches, sensors, nano and microlithography devices, nonlinear devices, metamaterial, or surface plasmon devices. So Fdtd is a direct solution to Maxwell's Curl equation, which is time dependent. There is no physical approximation. The problem is size is limited only by the computing. Time is broken into the discrete steps of delta t, and E field components are computed at t is equal to n into delta t. And H field is at n plus 1, plus 1.5 delta t for each computational step. Fdtd, the full wave Fdtd has a features that it can do the 2D, radial, and 3D simulations. It has a very unique features of non-uniform mass. So non-uniform mass is very useful when you have a device where certain portion of the device has a very little change in the index profile or the material profile. There, the grid can automatically be bigger, and where there are interfaces between two different index or index is changing, the grid size can automatically be finer. It has a full control of dispersion, nonlinear and anisotropic effect. It's a frequency dependent saturable gain model. Full wave Fdtd also has a Q finder, which automatically finds the cavity modes and Q factor. It measures the field profile, power, flux, energy, and so on. Also has a different frequency analysis option. This is a ring resonator, which is very popularly shown whenever there is an FDTD based tool. This is a high Q filter. So every time when you simulate, it will show the real-time propagation of the field. And let me show you, sorry, some example of FDTD. Now, in case of full wave, each of the tool in RSoft CAD will have different monitors and different measurement technique. So unlike a beam probe where you have to define the path and put the monitor into it, in FDTD, you just have to put the monitor, and they are the different type of monitor. So if you right click on this is a monitor. And if you right click on this, it will have various options what you want to measure, and you can select your measurement options. Now, and also the launch parameters is the same features available here. You can define your launch field here. In FDTD also, you can use the compute mode. That options will be available in all. So you can select, you can check whether your device, what you have designed, has the same refractive index profile what you intended to do. And when you do the simulation, the different window will open. And you can see, you can finalize the grid size, whether it automatically or you can manually do it. You can select different type of boundary conditions. You can select the whether you want to have the use the dispersion and non-linearity, what kind of polarization, then different boundary conditions, and what you want to have in the simulation options. So there are large number of options are available. Also, when you are simulating, it has a stop criteria. That stop criteria, there are different type of. One is after fixed time, you stop the simulation and output the result. Another is convergence, no limit. So until the field gets converged, it will keep on simulating, and stop at a particular limit or ask a limit and so on. Okay. What kind of excitation you want to use, continuous wave, pulse or impulse type of. So if you simulate it, also the full wave FDTD can have the parallel computing. So you can use the clustering option here, where since this requires a lot of computational resources, you can, in a LAN, you don't need any graphic card or anything. All the normal computers in a LAN can have can be used as a cluster, where the problem is divided between the different computers if you have the cluster license available to you. So if you or when you have the multi CPU in a processor, it can use that every CPU power while solving this problem. Okay. So let us just solve this, run this simulation. Now, as you can see, the time limit, since as till the time the field gets converged, it will keep on simulating. So unless it gets the resonance frequency, it will automatically keep on simulating. It will not stop. Once it gets the convergence, then it will stop and give the result. Okay, so now computation is completed and you can open the simulation results. This is what is the simulation, how the field is. In fact, we have not put the file prefix. That's why the other results are not available. In all the simulation windows, you have the option of putting the output prefix. So you can put the output prefix here and all your file will carry that prefix. So you can identify for the same structure, if with little bit modification, if you want to do the simulation again, you can identify the different data file for different simulation. So this is Fdtd, which has very versatile options. Next is the Bandsaw, based on the plane wave expansion method. Now, this is the only commercial full-featured tool for the PVG materials. And it uses the plane wave expansion method. It's a periodic nanostructure PVG are simulated using this tool. And it solves the Maxwell equation with assumption of the complete periodicity. The band calculations for the PVG can also be done with the Fdtd, and with Fdtd and PWE, you can also find the bands of the PVG material. The application of Bandsaw is 2D and 3D photonic crystal slabs, cavity problems, photonic crystal for band gap and index guided, or defect modes of non-strictly periodic structure, metallic and anisotropic structures. As I have mentioned, it uses either plane wave expansion method or Fdtd method to solve the solve for the band gap diagram. So when you are using only plane wave expansion method, when you buy only license for Bandsaw PWE, you will have only PWE. But when there is a Fdtd license, you can use Fdtd as well. So by using the Bloch theorem, it was modified the Helmholtz equation, and the goal is to find the frequency and mode function for each value of k in case of a Bandsaw. So from here it can be found that minimizing the above function, we can find the eigenvector L, and for each of the successive frequency, by minimizing and orthogonalizing against each other, against the previously found modes. To do this, we represent the unknown mode function as a Fourier series. We can find EUK from the iterative matrix solving technique. The advantage of PWE is it is very accurate and efficient for most of the periodic structure. The other technique can also be utilized for the complex devices. The disadvantage here is it cannot include the lossy material, and it cannot compute the complex eigenwave value for the decaying mode. Also, the refractive index must be the same for all frequency. So no dispersion. The Fdtd can also be used for the band solving procedure. And this is a procedure to run the impulse simulation with periodic boundary conditions at fixed K, compute the frequency response at that K, utilizing the time monitor and FFT calculation, use the peak finding formula to extract the location and frequency of the mode that fixed K. Plot the frequency information of modes that for that fixed K, and then go to the next K and repeat and so on, and you can find the band gap diagrams. The advantage of using Fdtd for the band gap calculations, that all material effects can be included. It can also include the loss and dispersion. The dispersion it's a very computational intensive because it's using Fdtd, and so it's a very time consuming, and it is difficult to set the band calculation due to launch and hand monitoring concern. It is also difficult in case of Fdtd being used for the band solving to distinguish between degenerated and nearly degenerated bands. So the band solve provides the band gap, blotch mode, and the band structure. Mode computation includes the defect mode. It can give the effective group index, group velocity, and the dispersion. And also it can plot the entire Brillouin zone. This is the diagram of just of the band solve simulation window, where you can select what technique you want to use. You can select the, you can set the eigenvalue, set the K path, grid size you can set, the lattice vector you can set because this is a periodic structure, and you can select the supercell size and the center of the structure. This is what Bandsaw will provide as a result. The T, it can calculate both T and TM mode band structure using, this is using the PWE method. Okay, so let me show you the software and simulate the band gap. Okay, we'll just for the now you can see this has solved the T by TM mode, and that you can decide. This is using the PWE method, and you are solving the both, that is hybrid mode. You can select the TE mode also and just check the TE mode, whether TE modes are available or not. Okay, so you can select both the polarization and what polarization you want to use for the calculations. Okay, so this is the band solve, and let's move on to the next method. That's Diffract mode, which is based on the rigorous coupled wave analysis. It is used for the diffractive optical element, for the data storage, for the micro lens array, for photonic crystals, and optical metrology and sensor and detectors. The RCW solves the Maxwell equation with assumption that it's a steady state, so there is no time data. It's a monochromatic, means one wavelength at a time, and the structure is periodic. Now, for the RCWA algorithm, the every incident light has, when it hits to the structure, it will diffract. We have the forward and backward wave, and each of this wave will have order, direction, power, and phase. And this is a full vector solution and starts with the Maxwell equation. Okay. Since the structure and field are periodic, we can use the Bloch notation to represent the E field. Substituting the Bloch notation into Maxwell equation gives the traditional eigenvalue problem. And this problem has a unique solution in each layer of the structure. The solution matrices are modes within each layer, and beta value are propagation constant. So once the eigenvalue is solved, the propagation through layer is computed. And there are so many methods to do this, but Diffract Mode is uses the modal transmission line. This is similar to the electrical voltage through the series of transformers. And because this method is very stable, so the solution is very reliable and powerful. It can simulate both 2D and 3D. It can take into consideration complex refractive index and the material dispersion. The output has a spectra of diffraction efficiency, reflected, transmitted, and absorbed power. Let me show you the software example. This is a filter. Now, each of this has a different property. There are 3 segments, different segments. Okay, and this is how the filter has been defined. Now, if you simulate it, this is the Diffract Mode simulations. And in advance, you can find out what is the mode number you want to go up to. You want to analyze the profile first, so you can do that. What algorithm you want to use, and go for the simulation. Okay, so since this is a filter, as you can see, it's a diffraction efficiency at this particular wavelength, 1.5426 micrometer. And this can also be used for solar cell simulations as well, the basic structure. Now, let us move on to the next. The FEMSIM, which is a finite element method-based mode solver, it computes the transverse and cavity mode. Transverse modes are 1 or 2D electromagnetic field, and cavity mode are 2D and 3D electromagnetic field patterns. Okay. FEMSIM is commonly used to compute the input modes for the device which are being simulated in beam probe or full wave. I mean, if you wish. Otherwise, normally the BPM based mode solver is used for mode solving. And it can, the FEMSIM can be used for standard and specialty fibers, arbitrary waveguide designs, index guided air core PCF, cavity mode calculations, and dispersion calculations. So you can also calculate the dispersion of PCF fiber using the FEMSIM and the post-processing of FEMSIM. So this is a basically tool to study the supported mode in variety of photonic structures. This is a FEMSIM equation, FEM equations. And FEMSIM has an advanced meshing scheme that improves the accuracy and speed. FEMSIM employs the full vector implementation for the high contrast, high index contrast material and high index contrast structures and low C structures, where particularly when you are using the BPM based tool, they are more for the low index contrast material. This has an advanced mesh option. It has a non-uniform grid. Non-uniform grid means the grid will automatically define the size based on how the material profile is varying. Grid also makes sure that at the boundary of the material, the grid size end is no grid is common between the two different material. So it makes sure that at the interface, the grid size grid is ending. So this is done all automatically. It subdivides the mesh. Now, if you can see here, when there are rapid variation, it can subdivide the mesh into different trigonal parts to improve the accuracy of calculations or the solutions at the area where there is a rapid variation in the material parameter. It also assumes, since this is being, when there is a periodicity in the structure, it reduces the simulation area to save the time and fast improve the speed of the simulation. This is an example of a leaky mode in multi-layer. Now, as you can see here, it finds the various modes. For each mode, it will find the real and imaginary value of the N effective. So the number of mode which you want to find you can define in the problem while you simulate. Now, this is a air core fiber. We're not going to simulate it, but this has already been simulated because the simulation itself will take few hours. But I'd just like to show you some results which has been simulated. Now, as you can see, this has been using the most, which we are going to discuss further. It simulates at the various wavelength and finds the N effective. Then there are dispersion also. You can also calculate the dispersion data for the waveguide using FEMSIM and the MOST. So here, the blue is the group velocity, group refractive effective index, and green is the dispersion value for this particular structure. Now here you have the option to fix the mass, how you want to use the mass in this particular problem, or how many modes you want to use, the mode option, how many mode you want to calculate. The number of modes to be defined, you can define here. The starting and effective, you can either put it as default, or if you are aware of previous results, and then you can define so to save that simulation time. And you can also define the maximum iterations the computation should do to find out a mode. Next is mode probe, or which is based on the Eigenmode Expansion tool. This tool is sometimes used where you have a bigger a structure. You want to have the time dependent information for the structure, and you can, because of the size of the structure, you cannot use the Fdtd. In that case, the mode probe can be used as a substitute tool to get the time dependent field information. So it uses the Maxwell equation, and it accounts for both forward and backward propagation and radiation mode. The model transmission framework to ensure that simulation is unconditionally stable. So it uses the MTL technique for the stable output, or the stable results. This mode probe can be used for the different options, different problems like surface normal gratings, plasmonic devices, sensors, filters, waveguides, photonic bandgap devices, or mode converters, or computing the coupling efficiency. Now, mode probe, how it solves the equations that when there are wherever there is a uniform refractive index, it considers that as a one region, and it divides the region into several step-like regions. And each uniform section is characterized by a set of eigenmode and corresponding propagation constant, or equivalently effective indexes. Now, mode probe uses the Fourier series expansion in the traverse direction. Inserting this into the Maxwell equation yields homogeneous system of equation for the coefficient. Effectively, it is recasting the problem into the form of a standard matrix eigenvalue problem. And to make the problem finite, the expansion is truncated to finite order. Otherwise, things will keep on running. So mode probe EME outputs are reflections and transmission of individual modes, total transmission, reflection and absorption, and far field output. I'll show you the This is an air groove structure, and when you simulate, you will have the grid options, what PML width you want to use. In the advanced, you can use the profile, analyze the profile, what kind of algorithm you want to use, and so on. So if I simulate this, as you can see, you receive the time dependent information of the field propagation, and after simulation, you will result the total reflection, transmission, and absorption data. Next is the grating mode based on the couple mode theory to solve the grating structure like FBG or head-drop filters, grating assisted coupler, or LPGs. I'll just skip this because now we don't have really good time to complete everything. This is also. Now, grating has a different analysis option. Either you solve the grating for using the Bragg condition or wavelength grid. So analysis parameter, either you fix the period or fix the center wavelength and define the this parameters. Okay. Next is using the mode. Either one can calculate the mode using the BPM based mode solver, or if you have a pre-calculated mode from the RSoft file, you can use that, like using the FAMSIM, you can input those mode to this grating and solve the grating problem. The output which is available in the grating mode is FWHM with at a half maximum, the peak amplitude and position, the stop band, left-right peak amplitude, and the period. All this, you can select whatever output you want from the grating mode. Also, this is the only tool where you can have cascading of multiple gratings. There are other grating simulation tools are available, but that cannot simulate more than a single gratings, which is not the case in actual use of grating, where you have grating in cascading to use them as a sensor. Also, this is the grating output, as I mentioned earlier. Then another option is there in the grating mode, that is synthesizing the grating. So you input the spectrum of what kind of spectrum you need, and it will design the grating structure for you. Okay, so here various options are available for the synthesis, and you don't have to draw the grating. You have to input the desired spectrum, and then it will synthesize the grating, and it will output the, if this is the input spectrum you want, then it will synthesize the result, and finally that it will output the structure with this synthesized results. This is a simple grating. Let's quickly simulate it. Now, as I said, this is a grating analysis. These are the analysis parameter, what you want to set. then what mode you want to use. This is auto calculations, or you can input the mode, and then in the spectral characteristic, what output you want to have, you can just select, and it will give you the output. So this is a very simple problem, and quickly, as you can see, whatever options we have selected, all of them are displayed over here. Next is these are all what is called the passive device tools, where light was just modified without creating or absorbing, or not absorbing, I mean, without creating the light. Light was just modified using certain structure. Now, laser mode is the tool which can be used to design the semiconductor laser, and it has it has a different CAD than the RSoft CAD. So here in the CAD, again, you have the library, material library. It has the predefined region like multiple quantum well, DVR, and so on. It also has a non-uniform mesh control. The material library also has a ternary and quaternary system of material, because the laser will use various kind of a dopant. This is the type of device which can be simulated using the laser mode. The Fabrication of VCSEL or DFD or photodiodes or modulators can be simulated. This is what the laser mode looks like. These are the different kind of a structure, and you can select the structure. Then there are very different creating the tools and simulation tools and so on. Okay, this is the now with different type of structure, the simulations are required to be done in a different way. Okay, in Fabrication, the propagation is in this direction. In the VCSEL, the propagation is in this direction, and in DFB, propagation is in this direction. Laser mode is a 2D simulation tool, so it simulates the laser in 2D. The output is LIV curve, transient response, and these are the other analysis features like energy band, carrier profile, optical spectra, and so on. Okay. So since this is a different tool, I'll just open one simple example. Of a DFB, so, and you want to simulate, and you can see what all physical mode what you want to have in the output, and select. So produce. Okay. So as you can see, it is now voltage versus current graph. It is producing. This laser mode is also used with the what we are going to look at the with active tools. It can also be used to simulate the electrical characteristic. Now this is selected. So This is the voltage versus current, and this is the light output versus the current. Next is the multi-variable optimize and scanning tool that's called MOST. This is a very unique tool available from the RSoft device tool. Here you can scan on multiple variables and automate your process of simulation to find out how the device performs at various parameter values. Okay. If you open MOST window, it will look like this. And I'll rather, yeah. Here you can see there are two parameters on which you are going to scan. Now, you can define the minimum and maximum values of the parameters. Once you define these scanning, it will automatically generate various output. And then you can select what output plot you want to display. You can also use various metrics.
Sir, sorry to interrupt you. We have 5 more minutes, then we'll go for QA session.
Yeah, actually, there are a lot of things remaining. But anyway, I'll try to quickly finish it in 5 minutes.
Okay, thank you.
Yeah. So MOST is a powerful tool where you can automate your simulation process. Also, you can automate your optimizing a device. Okay. If you want to study at what is the optimized parameter for a specific device that has been designed. Okay. It has also several advanced features like, as you can see here, you can calculate the dispersion from whatever results you have received in your optical simulation. It can also, you can also have the user-defined measurements, which are from the whatever available data. Okay. The MOST can also implement a user simulator. So the one example is given here, that when you want to calculate the both polarization, how to do that. Okay, for that you need to write the script. I'll just I'll just show you. Now, this is the coupler which we had seen earlier. In the MOST, once the coupler symbols are there, it will automatically will have, you can get them from here. Now, in this case, we are scanning for the separation between the two waveguide from this two value in this much increment at this much step. And then automatically, once you define this, it will define what are the available measurements. Then you can select what measurements you want to have. And this can also define various metrics which has not been. Then you have the advanced post-processing equations which you can write over here. Standard libraries are available in RSoft tools which you can use. Okay, I will not simulate this. Rather, I will quickly run through the different utilities since we don't have time. How can I? Okay, sorry. The LED utilities are for computing the extraction efficiency. LED utility, as I have mentioned earlier, the utilities are using the optical calculations from the main simulation engine. In case of LED utility, it uses the full wave for computing the far field, and then it will find out the various plots of the LED X-section structure. The solar cell utility to design the solar cell, it can use diffract mode or full wave for as a main simulation engine, and it can calculate the electrical. It can do the electrical simulation either by considering the solar cell as a ideal diode, or using the laser mode as a real what are the electrical bias and all that. Okay. Next is the it is a solar cell utility. Then this is the multi-physics utility. Different type of multi-physics utilities are available in RSoft tools. Thermo-optic, electro-optics, stress optics, and carrier effect. As the name indicates, they simulate the effect of either stress or electrical field on the index and on the material behavior. These are the different applications. Then there is a tapered laser utility, which is used for, as the name indicates, to simulate the tapered laser. Since tapered laser requires the 3D calculations, optical calculation, it uses the beam probe along with the laser mode to simulate the tapered laser. Then another utility is available in the RSoft tool is bi-directional scattering distribution function. So any light which is incident on the surface will have a lot of scattering. Now this scattering, particularly when you are simulating or designing a bulk devices, like say for example, LCD panel or LCD screen, TV screen. Okay, there you need to find out how the LED which are emitting the light diffracts, and because that will decide the quality of your screen. Now, the tool which are used for the simulating the TV screen, they are based on the ray optics, and ray optics cannot simulate, cannot give the complete information about the polarization and various diffraction characteristic of the incident ray. So there, the BSDF utility from the Photonics tools are used to gather the complete information about the diffraction of the light, and then convey it to the ray optics simulation. So in case of Synopsis, the RSoft tool with the light tools are used for this purpose. And the different applications like extraction analysis, LCD panel diffraction analysis, or the diffractive surface ray tracing simulations, AR, VR devices, and so on. So this is where the mixed level simulations are required. Another utility available within the beam probe is the AWG utility or Aero Waveguide utility, which are used for what is called the multiplexers and demultiplexers, and you can design simply by selecting how many input ports, how many output ports, what is the system of material you are using, and so on. Okay, this is all about the RSoft device and photonics active and passive devices. Now, very quickly, I'll run through the photonics system design tools. These are the OpSim, ModeSys, and bidirectional modules. What is OpSim? What is the system? Now, system in an communication system means the optical communication system means conveying the data from one electrical word to the another electrical word using the uh, medium of light. Okay. So what OpSim does, it has a virtual laboratory which consists of all the component and model required for designing the transmission medium and the channel. It can be used for any kind of simulation, any kind of optical communication system, long haul, short haul, data centers, and so on. In fact, this is OpSim is one of the base tool where you can transfer the custom PDK to the PIC tools using the schematic diagrams. Okay. OpSim also, you can have the co-simulation with the MATLAB and other simulation tools of the RSoft. You can co-simulate RSoft tools, RSoft device tools, and also the MATLAB, where you can make your own layer. These are the different applications of the OpSim. I'll just run through. It has a vast number of tools, models available, more than 600. It has a best fit laser toolkit. And it's like a virtual optical communication laboratory where you can simulate all your optical communication systems. It is the only tool where you have the dual simulation tools. It simulates all the non-linear and linear effect of the fiber and also polarization effect. It has very high accuracy. It has been proved and published. This is also again parameterized model. Each model has a parameter windows where user can define, or there will be a default parameter and user can define their own parameters also. Then in the post processing, you can find out all the electrical characteristic, optical characteristic, MATLAB interface. So you can define your model in the MATLAB and simulate. You can just in case when if you have a laser and you don't know the you don't have the complete parameter, you can find out using the best fit laser toolkit. Modes is a tool for the multi-mode fiber. Unlike OpSim, where mostly we are dealing with the sample mode fiber, single mode fiber. Multi-mode, in case of multi-mode fiber, it is also very essential to track how the field is propagating to the fiber, because there are more number of modes are traveling to the fiber. Okay. So this is used for the automotive applications or submarine data link where plastic fibers are used, or where there are high diameter fibers are used. Okay. Okay. Yeah. This is the bidirectional module for the bidirectional module for the OpSim, because in some cases where there are links are very short, particularly let's say the data center links or the PICs, where links are in order of the micron. So you need to simulate the back reflection from every joints of the waveguide. So there the bidirectionality simulation is required, and the bidirectional module will useful for such systems. Okay. These are some of the applications for bidirectional modules. Okay, yeah, just one last thing. Since the main theme of this webinar is PIC tools. Now, you may be wondering how this is related with the PIC tools. So, all the photonic devices which you want to design and implement in the PIC can be simulated in the RSoft photonics device tool using the S matrix utility, which we'll see next in the next webinar. You can define the custom PDK, export it to the OpSim circuit, which is similar to the OpSim bidirectional module, and also send it to the layout module, layout software called Opto Designer to design the PIs. Okay. So I think there is vast number of tools, so really we have to rush. Okay, fine. So if any questions, we can take it up.
Okay, okay. Thank you, sir, for excellent talk. And now we'll move to the QA sessions. We have a couple of questions in the QA box. I will address you one by one.
Yeah.
First question is that can we simulate meta surface in Synopsis?
Yes. Yes.
Yeah.
Yes, it can be.
Okay. And second is that in the same thread, can we simulate a ring resonator or microdisc cavity integrated with 2D material called TMDC, like monolayer MOS2 or WSE2? And how difficult in simulating monolayer material having 1 nanometer thick?
It can be done. It can be done using the full wave or mode probe, and it will not be one. I mean, size does not really matter as far as the simulation software are concerned. Okay, so if your structure is complicated or bigger in size, what matters is the computational resources. Okay, so it can be done.
Okay, so maybe it's asking about is 1 nanometer thick in vertical direction. So how this masses can address this nanometer thick material in the cavity?
Full wave, yeah, I understood. Full wave can do the 3D simulation. It doesn't. It can easily do the 3D simulation, but only thing is, depending on the complexity of the structure, you will require the computational resources. I like to just point out one of the trick example. One of the customer, they were working on the PCF band gap using the Fdtd. It was not a big structure, but the structure was so complex, they were using the high speed computers. I can give the name of the customer. So IISc, they had 8 computers in the land, and the one problem used to take almost 7 to 8 days. Okay, so complexity will decide how long it will take, but theoretically everything is possible.
Okay, okay, so thank you. And this next is the does required specific heavy workstation or computer system to run this Synopsis photonic simulation software? Or it can be.
Yeah, actually this is what I have been saying. It depends. Everything depends on the size of your problem. Okay. If the normal computer is there and your problem is not very complex, then it can do with any simple computer. I think most of the our customer, we have more than about 500 licenses of various tools. And except few, most of the people are running, most of the users are running on normal computers with maybe, I mean, the higher RAM is required. Better the computer, it will give you better, I mean, faster calculations.
Okay.
But then again, as I said, will depend on what kind of problems. So it is widely open, but for the normal use, normal computer will be good enough.
Okay. Okay. And next is, can we import desired design structure in RSoft for the simulations? Or how it can be done?
As I said, see, these I am not really sure about if you have uh, designed some structure somewhere else, and if you want to implement, but any then if it is GDF file or something, like number of file formats are supported, but you can draw any kind of a structure in RSoft CAD. As I had shown, number of various complicated structure can be implemented.
Okay.
Is it I'm not sure whether that is really I have answered.
It's maybe asking like some structures might not be available in the library of your Synopsis software. They want to import it by designing somewhere else, like Python coding or some other CAD design.
Yeah, see, this is what I said in the beginning. Any kind of a complex structure can be designed in RSoft. There is no RSoft. If you have seen the CAD tool, there are simple structures are available. Okay, so but you can use those to define and design any type of complex structure, any type of complex structure. So really, I mean, you have to use some little bit creativity to design a structure, but you can always do that. But probably, yes, if something has been designed outside using Python or something, that can also be imported.
Okay, I hope this answered. And next question is, what is the structure for band structure method that is simulated? Is it a PIN modulator?
No, I didn't get that.
I'm repeating the question. What is
Yeah,
the
yeah,
structure?
I'm seeing that also, but I don't understand the question. That band
Maybe
structure method.
some parts missed, some parts missed in the typo.
What is the structure for the band structure method that is simulated? Is it what we have been what we have simulated? He's asking, or I'm not sure.
Maybe some word is missing here to correlate this.
Yeah,
We'll
yeah,
skip,
yeah.
move to the next questions.
Yeah.
Can we bring stress result of an NSS CSV file to RSoft multiphysics tool?
I am not very sure about which tool you say.
RSoft, he's saying like,
No.
can we bring NSS
Can.
numerical, maybe NSS numerical CSV file to?
Okay. Yeah. A stress result of yes, actually I'm not much because we are not sure how the NSYS CSV file, because see, when you want to bring in some result from one software to the another, the only issue is you need to modify those results with the same grammar as the tool in which you are importing that. Okay, so since you have the data in CSV format, I'm sure if you look at the RSoft file grammar, then it can be done. Only thing is there is no ready-made utility where it can read the ANSYS CSV file. But it is possible by some manual efforts by converting that ANSYS CSV file into the RSoft file grammars.
Okay, I hope this answered. Next question is, I will take one more question, then we'll go for end of the session. Can we implement laser mode software and RSoft together to solve a complete integrated photonics and electronics circuitry without switching to and fro every time?
See, I think the purpose of laser mode and RSoft tools, one is simulating the passive devices, another is simulating the active devices. But in certain cases, okay, I mean, if you are talking of complete electrical simulation, say for example, you want to design a photodiode. Okay, so now photodiode, optical and certain electrical simulation can be done using the laser mode, and maybe you need to use RSoft tools. Yes, it can be, the files are interchangeable, but still these tools are for the optical domain. The laser mode is also not covering the complete electrical domain too. This is the electrical domain of optical, which is it is covering. So Synopsis as a whole has a solution for this. All the RSoft tools, in fact, this is we are going to cover in the next webinar. All RSoft device tools can be co-simulated with Synopsis TCAD, Centerus. Okay, there I believe the complete, without going back and forth, you can simulate by running the Centerus TCAD and invoking the RSoft CAD tools. You can simulate the complete device, optical and electrical.
Okay, so most of the question I covered, and remaining few question I will compile and send to the speaker. They can answer and upload it in the chapter. Now we'll move to the one announcement and we'll end the sessions. Sir, can you share the screen? I have to announce some things.
Yeah. Okay.
Yeah, okay, thank you, sir. So in the continuation, the advanced technology of the Synopsis next part, that is PIC suite and auto compiler, will be addressed by the another expert engineer, Mr. Tang Yuang. So he will deliver the talk on 25th August in the 3 to 5 p.m. And for the available link and everything will be uploaded in the all the social media platforms. You can go through there and get the registrations, and we'll also update in the dedicated Photonics chapter IT Bombay chapter. And the today all the recorded video will be available in our YouTube link, Photonics chapter IT Bombay, by tomorrow. So you can anytime you can visit and access and watch it. And now it's about to end the session. Thank you, sir, for the accepting of the invitations and joining today to deliver the talk on excellent PIC simulation design by Synopsis RSoft software. And in the future, we are looking for the next collaboration for another talk. And for the audience, please register the next talk on 25th.
Thank you. Thank you, Kishore.
Thank you, sir. Have a
I just wanted to make if somebody wants PDF of this presentation, they can just send an email to you or to me. We can send it to them.
Sure, sir. If I get the email, I will forward to you.
Okay. Okay.
Sure,
Thank you.
sir. Thank you. Have a nice day.